So in the previous class, we have studied what is an intrinsic semiconductor, how the conduction of a semiconductor, intrinsic semiconductor, can arise as a result of motion of electrons in the conduction band as well as motion of holes in the valence band. And we also have studied what are extrinsic semiconductors, what is an N-type semiconductor, P-type semiconductor, and we also have seen that when an N-type semiconductor and P-type semiconductor is joined together, then in the vicinity of the junction, how a depleted region is formed. And today we will see as to how appropriate biasing of this junction allows the performance of this PN junction as a diode. So let us first reverse bias this junction. Reverse bias means the N side of this junction is connected to the positive terminal of the battery, and the P region, the junction, is connected to the negative electrode of the battery. That is called reverse biasing of the PN. So let us see what happens in reverse biased operation. So we connect the N side to the positive terminal of the battery and P side to the negative terminal of the battery. Now, the moment you have connected, there will be a momentary flow of current as the free electrons from the N side, N region, and the free holes from the P region flow away into the battery. So they will flow away into the battery and they will neutralize each other. This quickly results in the depletion of charge carriers on either side of the junction. So charges will be depleted both in N region and in P region. And thereby it will cause stoppage of the flow of any further current through the circuit almost instantaneously. The moment the circuit is connected, the battery is connected, there will be a momentary flow of current. But after that, there will be a complete stoppage. However, the presence of some residual current, which is the reverse current, cannot be ruled out, arising from the creation of occasional electron-hole pairs owing to the thermal fluctuation that is inevitable. You see, this is my P junction, this is N, and this is P. Now, in the semiconductor, intrinsic semiconductor, if suppose this is the valence band and this is the conduction band. So due to some thermal fluctuation, that is, if suddenly there is a slight increase in temperature, the electrons will have more energy and therefore the electrons can jump over from the valence band to the conduction band. So that will create an additional electron here and hole here, electron-hole pair. So because of that, there will be some again flow of current, reverse current. This is called reverse current. This thus represents operation of the PN junction under the reverse bias condition. That means after some very initial flow of current, immediately as you connect this battery, there will be stoppage of any further flow of current, although there is a possibility of some flow of some reverse current, which arises from thermal fluctuation, which will result in direct crossover of the valence electron to the conduction band, resulting in flow of some reverse current. So now let us explore the forward biasing of the PN junction. So we now reverse the polarity of the battery. So then N region is connected to the negative terminal of the battery, and P region is connected to the positive terminal. The battery now clearly pumps electrons into the N region and holes into the P region. These holes and electrons continue to meet and annihilate each other in the junction region. So these holes, electrons which have been pumped in this region and holes in this region, they will now continue to flow and annihilate at the junction, maintaining a steady flow of current through the circuit in this configuration known as forward biasing. So in the forward biasing case, this will allow a flow of current. And the higher is the battery voltage, the greater will be the magnitude of the forward bias current. The more electrons will be pumped in the N region and more holes will be pumped in the P region if you increase the voltage of the battery. So that will increase the magnitude of the current. The voltage current characteristics of a PN junction diode operated in both reverse and forward bias condition is shown here. This is forward bias, so the current is increasing with voltage. As we increase the voltage, current will continue to rise. And this is the reverse current, reverse bias current. The origin of this I just explained. So having acquired this background knowledge of semiconductor physics, we are now in a position to appreciate the working of a semiconductor diode as an emitter of light, both ordinary as well as coherent. So let us now focus on light emitting diodes. Let us take a closer look at the creation and annihilation of an electron-hole pair in a semiconductor. So you have this is the valence band and this is the conduction band. So in a semiconductor, it is easy for an electron with a slightly elevated temperature for an electron to jump from the valence band to the conduction band, thus creating a hole in the valence band, and the electron appears in the conduction. We know that a minimum amount of energy equaling the band gap energy. So for this, the minimum energy which is required to be supplied to the electron is just this band gap to be imparted to a valence band electron for its excitation to the conduction band, leaving behind a hole in its original location. Although the thermal energy that is always present normally facilitates this excitation, it can also be achieved optically provided the photon energy exceeds the band gap energy. Now, of course, the thermal energy that is always available, and if you increase the temperature a little, there will be more thermal energy, so it actually facilitates the electrons crossing over from valence band to the conduction band. And the same energy can also be provided by photons. If the photon has energy, that is photon's frequency is such that photon's energy, which is hν, if this hν exceeds this band gap energy, then the electron can absorb this photon, and as this photon's energy exceeds the band gap energy, the electron can cross over from the valence band to the conduction band by absorbing this energy. When an electron and hole combine, so like a photon, when absorbed by this electron, and if the photon has energy more than this band gap energy can excite an electron from the valence to the conduction band. Similarly, when an electron, suppose this electron jumps down to the valence band, and the electron and hole then would combine and annihilate each other. So what basically happens is that an electron from the conduction band falls into a hole and they annihilate each other at the valence band, and the two nullify each other. That is the annihilation. So if they nullify each other, then what will happen? The excess energy that is released when the electron jumps down into the valence band can be emitted as a photon. You see, like when a photon is absorbed, suppose there is an electron here, and if a photon comes and this electron absorbs this photon, it goes off here. So the electron climbs up to the conduction band and a hole is created. So this needs a photon of appropriate energy to be shown onto this, and then the electron will absorb that photon and will jump to the conduction band. Similarly, when this electron can drop down to the valence band and combine with the hole, this energy which is released when the electron jumps down from the conduction band will give rise to the emission of this photon. This is just the reverse process. So this excess energy that is released when the electron jumps down into the valence band can be emitted as a photon. So that means what? How this photon has been emitted? So thus, upon forward biasing, the PN junction allows a flow of current, while the holes and electrons continue to recombine at the junction and nullify each other. As the holes and electrons, they combine, they annihilate, they combine at the junction. They combine at the junction and annihilate each other. So that basically means that an electron is falling down onto the hole and they're recombined and annihilated. So the extra energy, that is the energy that is released, is emitted as photon. So then, upon forward biasing, the PN junction allows a flow of current while the holes and electrons continue to recombine at the junction and nullify each other. This essentially means that recombination is nothing but the conduction band electron literally jumping down into the hole in the valence band. And if the excess energy of the electron is released as a photon, the diode can then be said to be a light emitter. That means diode is emitting light. So you are actually using the current, and this current is being converted into light by you are taking advantage of this PN junction to produce light from the electricity. We can thus say that a PN junction, when forward biased, is capable of emitting light. There is, however, a catch here. The electron-hole transition is radiative, that is, it can emit light normally for only direct band semiconductors. So what is a direct band semiconductor and what is an indirect band semiconductor? You see, without going into any more detail, let me mention that in a direct band semiconductor, direct band gap semiconductor, the total momentum of the electron and hole do not change as they recombine. The transition only involves a change in the energy that is carried by the emitted photon. See, as the transition takes place, that is, the electron comes down and combines with a hole. This process, in any such process, both the energy and momentum must be conserved. In a direct band gap energy semiconductor, the conservation of momentum is automatic. It is intrinsic to the property of the direct band gap semiconductor. And the deficit of energy, that is when the electron falls back onto the, drop down onto the, from the conduction band to the valence band and recombines with a hole, the energy, that is the deficit of energy, that is the energy balance, is maintained by the formation of the photon. The extra energy is carried by the photon. So in a direct band gap energy, this transition results in both conservation of momentum as well as conservation of energy. Conservation of energy similar just comes from the formation, creation of this photon. So in direct band gap semiconductor, this process can be quite possible. On the contrary, in an indirect band gap semiconductor, the total momentum of the electron and hole changes as they recombine. Conservation of momentum is not possible if the excess energy is released only as a photon. The extra energy, if it is released only as a photon, then the conservation of momentum is not possible. Momentum energy is of course conserved, but not the momentum in an indirect band gap. The electron needs to pass through an intermediate state to transfer momentum to the crystal lattice, and in turn the energy is dissipated as heat instead of light. So in an indirect band gap semiconductor, creation of light is not possible because it would violate the conservation of momentum. So this is not possible, such a process. Silicon, the best known semiconductor that serves as the building block of miniature electronics today, is unfortunately an indirect band semiconductor. Nature has always not been very kind, and thus does not make a good light emitter, hence a light emitting diode. Other semiconductors such as germanium, gallium phosphate, aluminum phosphate, aluminum arsenide also have indirect band gaps and thus perform poorly as emitters of light. Some of the notable examples of a direct band gap semiconductor as gallium arsenide, gallium antimonide, indium antimonide, indium arsenide, indium phosphate, indium antimonide, of which gallium arsenide has the distinction of emerging as the very first light emitting diode. And also, as you would see later, that the very first semiconductor laser also made use of gallium arsenide as the active material. So with this background knowledge, let us now switch over to diode lasers. So long we have just studied diode as an emitter of light. There the light is emitted in every possible direction. So the emission from an LED, light emitting diode, is spontaneous in nature, and the emitted light is therefore ordinary and spreads in all possible directions. So if we draw this is PN or P junction, this is N P region, this is N region, this is the depleted region where the charges actually recombine and light is emitted. Light is emitted in all possible directions. So here I show the emitted light in two dimension, but basically the light is emitted all around for the entire 4 pi solid. So this is spontaneous emission. So how then we can make a diode, make an PN junction work like a diode? It is not difficult to figure out that a light emitting diode can be converted into a laser by realizing in it the condition of population inversion and simultaneously ensuring the presence of optical feedback. That is, basically we have to integrate this population inverted medium with a cavity. How we ensure population inversion? The population inversion can be ensured by appropriately increasing the pumping current so that the rate at which electrons fall into the holes and recombine exceed the rate at which electrons at the valence band can jump into the conduction band by absorbing photons emitted from the recombination. So you see, you have a this is the valence band, and this is conduction. Now, as you are pumping the current, so the electrons you are creating, as you are pumping the current, you are creating holes and electrons in the holes in the valence band and electrons in the conduction band. So you are actually producing these holes and electrons, and these electrons are also at the same time is falling back into the holes and absorbing the photons which are being created as a result of electrons falling back onto the holes. And these photons which are being created can also be absorbed by these electrons here, and the electron will jump up to the excited state, conduction band, and create a hole. So in order to create population inversion, the rate at which the photons are being created must exceed the rate at which these photons can be absorbed by the electrons on the valence band, which will create holes and electron pair. Only when this rate of generation of photons will exceed the rate at which the photons will be absorbed, will there be a state of population inversion. And when this would be integrated with a cavity, it can actually result in emission of coherent light. So then, the population inversion can be ensured by appropriately increasing the pumping current so that the rate at which electrons fall into holes and recombine exceeds the rate at which electrons at the valence band can jump into the conduction band by absorbing photons emitted from such recombination. Feedback can be provided by placing the device inside an optical cavity. Nature has been kind here as the refractive index of semiconductor material is usually very high. For example, the refractive index of gallium arsenide is 3.6, which is an extremely high number, and the Fresnel reflectivity is about 36%, because you know that the Fresnel reflectivity, so this is my gallium arsenide, and this is air. So this is one phase and this is the other phase. So what will be the reflectivity that this phase should offer when light falls on this? Light that is created in the junction will fall on this. So what will be the reflectivity, Fresnel reflectivity? We know that it is n minus 1 whole square divided by n plus 1 whole square, where n is the refractive index of gallium arsenide and 1 is the refractive index of the surrounding medium, which in this case is there. So that can be taken as 1. So n is, as I said, is 3.6 minus 1 whole square divided by 3.6 plus 1 whole square. So this, if you calculate, it will come to about 0.36 or maybe 0.35. So that means the Fresnel reflectivity is 35%. That means if 100 photons shines onto this surface, 35 of them would be reflected out of 100. So this reflectivity, that is 35% reflectivity, is good enough. If you can create high gain, that means if you can create very high population inversion, then lasing can sustain here. Because we know that for lasing to sustain, suppose this is the gain in frequency, and this is gain. And for 35% reflectivity, the loss line can be located pretty low. So that means the gain can exceed loss. So the lasing will be sustained. So that's what. Feedback can be provided by placing device inside an optical cavity. Nature has been kind here, as the refractive index of semiconductor material is usually high, providing quite high reflectivity, that is about 36%. Cleaving the end faces, which are perpendicular to the laser axis, this is the laser axis, therefore allows much of the light created at the junction to be reflected back and forth. This will help meet the threshold condition for lasing in many cases. Cleaving means to make the two surfaces optically flat, which is essential for making them perform the role of the cavity mirrors. As it occurs in any other laser, a fraction of the spontaneous emitted photons in the junction that travel along the axis will initiate the stimulated emission. That is, will seed the stimulated emission, causing amplification of light. You now know it very well that the stimulated emission actually is seeded by the spontaneously emitted photon which travels along the axis. For low gain lasers, for lasers which gain is low, or when an unidirectional laser beam is essential, because here the laser beam will be emitted in both directions. So either when the gain is low or when an unidirectional beam is essential, the reflectivity of the faces can be manipulated by appropriately coating them with dielectric layer to give the proper reflectivity that will ensure that the loss is less than gain, and therefore you can still affect the lasing in such cases. I think I will stop here today, and tomorrow we'll begin right from here.